boards. I got about 50 solder boards in today. There's two sizes. So they're laid out. They have the same connection pattern as the white boards, except they're in solder format. So it's a set of holes that are set up for P-dip, and then a bunch of connectors out like this for soldering to. So it takes P-dip, makes P-dip translation from whiteboard to solder board very easy. There's two sizes. There's the little size and the big size. The little size is about $2 on budget, and the big size is $4 on budget. Both of them are cheaper than a whiteboard. Clearly, if you only need to make a few connections, you could take one of these boards and cut it in half and save yourself a little money. As long as you don't completely mangle the other half so that somebody else can use it. Let me remind you that if you're soldering, or you're even sitting at the solder table, you must be wearing safety glasses. No exceptions. Somebody watching you solder, they have to be wearing safety glasses. Any questions about final project? So there were exactly 4 groups in lab this morning. The level of anxiety is not very high. We're 1 month. Now you're 1 week into final project because it actually started at the end of lab last week, right? And so you're now 4 weeks away from demo. You should be panicking. All right? Like, the lab should be full in the morning. It's on the schedule. Okay. Again, any questions about final project? Any questions about serial peripheral interface I talked about last time? It's a very simple protocol. Byte serial, no addressing. It's all done by chip select. It's rather straightforward. I want to talk a little bit about I2c Protocol today. And unlike every other topic I've talked about so far, I've never actually interfaced an I2c chip myself. And so I'm hoping there's no bogosities in this, but I hope what I say is true. I2c on this particular chip can run with a 7-bit address space, so 128 devices on the bus. However, most devices that you buy have a pre-programmed address. And so you may not be able to put copies of it on the bus. Now, one ADC that I saw from Analog Devices came in 3 different variants. Address 1, address 2, and address 3. So you can put 3 devices on the bus. The ROM that I'm going to talk about in a little while comes in 8-pin PDIP, but 3 of the pins are dedicated to the lowest 3 bits of the address, so you can put 8 different devices of the same kind. The top bit is hexadecimal A 1010, and then the 3 lower bits of the address you get to choose by strapping pins to either VCC or ground. Strapping them high or strapping them low. So there's a lot of address space, but you have to sort of juggle devices to maybe to use all of it. Maximum speed on our architecture is about 400 kHz transfer rate, bit rate. So it's not blindingly fast. Probably an order of magnitude slower than SPI. There's lots of requirements on the electrical requirements for the I/O pins that drive an I2c bus, luckily you don't have to worry about that. The pins are automatically slew rate limited, for instance. That is to say, they do not change state very fast as required by the protocol. Also, the hardware ignores spikes that are less than 50 nanoseconds wide, so that bogus data caused by noise gets suppressed at the pin level before your software has to deal with it. Yeah.
Why do so many accelerometers use this?
Well, it's cheap, but and it's been growing in popularity probably because it's cheap, and it saves one wire, one pin over SPI.
But you're saving information from being transferred too.
Yes, that's true. It's slow. It's slow. So the configuration would be you have several devices, D1, D2, DN, and so we'll call this the SDA data line. And then you have a separate line. You have a separate line which is going to be SCL. So that's the clock line. Data line is bidirectional. Clock is determined by the master. So one of these devices will be a master. And the most usual failure mode for student projects, my I2c bus doesn't work, is that the students forget to hook up the pull-up resistor on these, which is required. Now, let's say the master is running at 5-volt power supply and the other devices are running at 3.3. The VCC you use on the bus should be 3.3, because that will protect the I/O of the 3.3 volt devices, but it'll still make the CMOS threshold for a 1 on the 5-volt device. Barely make the CMOS threshold for a 1. So, I2c does not require level shifters for mixing 5-volt and 3-volt devices, although you do sacrifice a little noise immunity on the 5-volt device. But it does require a pull-up resistor, and this must not be, in spite of what the datasheet says, you should not use the internal pull-ups on the Mega 644. Rather, you should choose these according to the spec. Now, a good starting point would be to start with 5.1K or so. Around 5K, 4.7K, 5.1K, something like that. You may have to go lower, you may have to go higher, but you could start there.
Why is that? Why shouldn't we use those?
Why shouldn't you use the pull-up, the internal? Because they're too high resistance. They're about 100K, and they don't give you enough noise immunity. So, you say, well, what do the output stages of these things look like? And it turns out that what they look like is one CMOS transistor hooked to ground, and then just a pin that comes out to either SDA or SCL, and there is no pull-up. There is no positive source hooked to the pin. Rather, that resistor is the positive source for all of the chips that are connected. which suggests that the more chips you connect, the smaller the resistor should be.
I should mention if anyone who has noise issues or they find 2.5 volt devices, the troubleshooting can be achieved with compute resistors. There's a really good application that I would really to actually send out. Not that
Give me the link or the PDF or whatever, and I'll put it up on the Facebook page.
I've noticed that some UART communication requires a pull-up as well between microcontrollers sometimes. I'm assuming it's the same behavior.
Probably, this is for UART?
Yes, but usually only on the TX line.
It's probably because it's open collector or open drain or whatever you want to say here, but I don't know for sure. It depends on the device. So these are all open drain devices, and the advantage of that is that you can, it's called a wire and, you're hooking them all together. Any one of the devices can pull the bus low, but if nothing is happening, the bus is high.
So what should the data direction should be set to 0?
Say again?
I mean, like whatever port you're using, DDR-X should be set to.
I think that the data direction register is not important because the I2c busmaster sets it the way it likes it, I believe. So there's special hardware. There's special hardware that for the I2c pins, and I believe that if you look at the spec sheet that the I2c drivers take over the I/O pins when you turn on the unit.
For the whole port or just those?
For those 2 pins.
Okay. And it's called, is it TWI on the data sheet?
I'm sorry, yes. In our data sheet it's called the TWI interface because I2c is a trademark. So 2-wire interface is the non-trademarked version of I2c. Same protocol. All right, so we have then, if we look at the waveforms here, let me say before we look at the waveforms that the protocol, the data protocol that's being sent over this bus allows multi-byte transfers. So one device, say D1, can say, bus is mine. And then it can send a byte. Then it can wait a while. Then it can send another byte. And once it says the bus is mine, nobody else can send until it says the bus is not mine anymore and gives it back. So there's a protocol for requesting ownership across bytes. So you request ownership, then you send a bunch of bytes, or receive a bunch of bytes, your choice, and then you release it, and then somebody else can request ownership. So there has to be a way of signaling data. Oh yes, and because this is an address system, every device has an address, there has to be a scheme for sending data over the bus, separately sending addresses over the bus, and separately sending it's a mine, it's not mine over the bus, which is referred to as start and stop in I2c, or TWI. So the way you signal all this stuff is, if this is S clock and this is data, then the data line has to be stable at either a high or low value before the clock is valid, before the clock is high. So it has to be stable before the clock is high and after the clock goes low. So the data has to be stable all the time the clock is high. That's used to signal both addresses and data. By the way, each packet, each bit packet, even though it sends it 8-bit data, 7-bit address, 8-bit data, every data packet is 9 bits because the 9th bit is reserved for an acknowledge bit back from the receiver. So the transmitter sends 8 bits, and in the 9th bit time, the receiver acts back to the transmitter to say, I got it. The way you signal a start or a stop, this seems awfully twisted to me, but the way you signal a start or stop, and these slope lines are to suggest that the rise times are specifically slew rate limited by design. The way you signal a start is to drop the SDA line in the middle of a clock. So this is SCL, CL, and this is SDA. We drop the SDA line in the middle of a clock, and that is a start condition. Okay, I get the bus. If we raise the data line in the middle of a clock, it's a stop condition. I'm releasing the bus. So a typical transaction, a typical data transaction is going to be to send a start signal, send a start, then send address and the read-write request. So we're going to send an address, which is to say which device, the master is going to typically do this, which device do I want data from, or am I going to send data to? So we send an address and a read-write command. So the address is 7 bits, read-write is 1 bit, and then the ACK coming back is 1 bit for a total of 9 bits. So then we send or receive data (8 bits plus ACK) unless it's the last byte, and then we send a NAC, a NOAC. And then we send a stop. This can be repeated. It can be multiple sends and receives. But once you set up the read-write, you have to do either all reads or all writes. You don't get to mix them. All right. So if you say you give it an address, you say we're going to read, then you can do multiple reads, but you can't mix in a write with that. Well, what happens? Let's say in a ROM, you want to send an address, which the ROM has to read in, and then the ROM is going to give you back some data, and so you want to have a write linked to a read, and you don't want that interrupted by some other device getting control of the I2c bus, and so there's another command called restart. It says, I'm keeping control of the bus, but I'm going to restart in read or write mode, which is different than my last read or write mode. So there's start, there's send address, send receive data, there's actually another command, restart, and then there's stop. And you think this is complicated? It is. And this is going to be the first peripheral for which I do not talk about the control registers directly, because it is such a mess that nobody manipulates them by hand. Well, the poor guy who wrote the library did, but so I'm going to talk about the library that manipulates the registers, which you're probably not going to touch. Yes?
Let's say you have 2 microcontrollers on one data bus. Can you switch between that?
You can, yes. There is a protocol there is a protocol for handing off who is the master of the bus. And the library I'm going to describe, which was written by a guy named, Peter Fleury, doesn't do that. So you have to write that. You'd have to add that function to his library. So this is pretty cool. It has kind of a heavier duty protocol kind of feel to it than the kind of low level stuff we've been talking about, because there's multiple states for the bus, which are controlled by a big state machine that's running in each device. So let's see. Protocol. So what are the so if you Google up I2c Peter Fleury, Fleury, you'll get the web page which describes the library I'm going to talk about. It was also used last year for one of the projects which was called Face Access. The Face Access project last year was a face recognition system for a kind of a biometric door lock kind of thing. Code is linked up here, but the full explanation is here. And the commands that he wrote, for instance, void I2c init void is it bit twiddles these low-level registers, and you can follow it, but you got to really want to. Void I2c stop takes no parameters. Then there's a car I2c start that takes one parameter. Wait a minute. It's got to give address plus read write. Well, it turns out that what this car is the address plus the read write bit. So the top 7 bits are the address, and the bottom bit is either a 1 or 0 for read write.
Is the return acknowledgement?
The return, yes, thank you. The return is either a 0 if it's accessible, and a 1 if it is if it failed. There's also a car function I2c rep start for when you want to keep control of the bus but change the read-write mode. And you have to reissue the address with the other read-write bit. Otherwise, there's no reason to do a rep start. There's also a void I2c start wait with a character variable which is the usual address plus read write. And this will stall until an acknowledgement occurs. It will stall until the system is valid. If it never goes valid, it never returns. And of course, I2c write, which takes a car data, returns a, it's actually a character function which returns a successful, unsuccessful, and then there are two variants on read. There's a read ACK and read NACK. Read with acknowledge means that you're going to ask for an acknowledge and then ask for more data. A read NACK means read one byte and then stop. So there's car I2c read ACK void, which returns the actual value of the byte. So this is the value that comes back, value of the data. And then similarly, an I2c read NAK void, which returns the last byte of a read and issues a stop condition. Any questions? So before I do an actual code example now, let's talk about, we have to know what device we're interacting with. Yes?
Yeah, I'm wondering because like devices other than the master one, like send like this kind of net, or it's only like the master's capability.
Master does that.
Okay.
Now you could, with multi-master systems, you could have any of these devices be a master, and there has to be a trade-off between them. But for virtually everything you're going to do in here, you can get away with one master.
Is the start wait command, is it just supposed to get an acknowledgement of that? Does it continue to try to send out the
Yes, it doesn't resend until it succeeds.
Okay, does the start do the same thing? The I2c start?
No, it returns either a success or a no success.
Okay, so that's a single
That's a single try.
It's not going to just send it out once and continue to wait. It'll keep sending it.
Yes. All right, so specific device I'd like to do a demo or to write some demo code for is a 24C02 ROM, EEPROM. So this would be something you program either in the system or outside of the system, but then retains data through a power cycle. This happens to be 8-pin PDIP. So the layout is E0, E1, E2. These three are the low 3 bits of the address and have to be tied either high or low. So you can have a total of 8 devices 8 EPROMs on any but one bus. Ground. VCC is pin 8 as usual. Mode. SCL and SDA. The mode has to do with, you can use this in a non-I2c mode, and we're going to ignore that. So the high order, as I said, the high order byte is 0xAX. So the high order byte is 1010. High order nibble is 1010, hexadecimal A. So did these just appear here, or am I just clueless? Oh, okay.
Yeah.
So you just appeared here.
Yeah.
All right.
It took me a while to get up here for a minute.
Wow. Again, this is 0 hexadecimal A unknown. So this is 0xA blank 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 blank. We don't know what that is because this is E2, E1, E0, and this bit is read or write. That's the address, the 7-bit address. So you can choose one of 8 addresses according to those 3 bits. So now we can actually write some code. So let's say we wanted to write to this and then read back. So we want to write to the device, write a byte to it, and then read it back again, show we can do it. So the first thing we're going to do is define a control byte or an address byte, which is 0xA. Okay, we're gonna set this up so we have 001 here. So we're going to call this device A2 on the bus. First thing we need to do is an I2c init. Which turns on the appropriate pins in the appropriate way and sets up a couple of registers. Now we want to write an address, so we have to do an I2c start. We're going to do a start wait because we don't know what state the ROM is or how fast it is. And we're going to say the parameter here is going to be address plus a constant, which is thoughtfully defined by Peter Fleury as I2c write. And we're adding that. And then once that returns, then we are ready to write the address in the ROM from which we want to write new data, into which we want to write new data. And so we're going to do an I2c write with a byte which is the ROM address. Not the device address, but the specific 1 out of 256 locations that you can write in the EEPROM. And so we'll say give it a value of 05, completely arbitrarily. So position 5 in memory is going to be written with write O. Well, what do we write there? FA. And the order of these commands depends upon the protocol that the ROM expects. All right, so you have to read the data sheet to figure out the protocol the ROM expects for defining an address and then writing data. So this sets up the write. This sets up the address within the ROM. And this sets up the data to be written into the ROM. Then we want to do an I2c stop. So now we're going to read back what was in location 5. So we're going to say an I2c start wait from address plus I2c write. And what we're going to write there then is once again the address I2c write 0x05. But now we need to read back from the ROM. And so we have to do a repeat start. We have to do a rep start because we want to maintain control of the bus. We have to change from write mode to read mode. Right, we're in write mode now, so we have to do an I2c rep start address oops, there's the plus I2c read. And then say value is equal to I2c read, and we only want 1 byte, so we're going to issue a read NAC. And then just for obsessiveness, in the example code, I2c stop was also put in. I'm not sure that's necessary because I think the NAC, the I2c read NAC issues a read stop. Why do I have to do a rep start here?
Well, why can't you just go from I2c stop to I2c rep start? Why do you have to start waiting?
Because you have to give it the address you're going to read from. So the protocol for the ROM says, give me an address, and I'll either, if we're in write mode, I'll write that address. If I'm in read mode, I'll send it back. Is there a repetition mode? So what you're saying is there a mode where it stores the most recent address and uses it again?
Well, I guess more of what I was thinking was it's like if you do I2c stop, why can't you just do I2c rep start and then like an I2c read something address?
Because you have to write the address.
Alright, so
It depends on the device. That's completely device dependent. And so my next sentence, when you held up your hand, was going to be that the hardest part of this is reading the data sheet for the device you're going to control, because it itself is some complicated state machine that goes through a whole bunch of gyrations. A ROM is pretty easy. You can read from spot, you can write to a spot. How about a video camera where you could read any spot on the image? Or you could start a new acquisition of an image, or stop an image, or do one line of an image. And so then you have a very complicated state machine with lots of commands. And the hard part of this is to understand the device you're controlling over the bus.
So let's say you were going for ranges of data or something. Is there like a closet for access?
You might have to. And this particular ROM, by the way, does support 8-byte bursts. And so you can put it in repeat mode, give it an initial address, and then do 8 reads in a row and get 8 bytes out.
But the Mega's going to operate much quicker than this bus can respond.
The Mega is much faster than the buses can respond. Yes, because this is running at 400 kilohertz. And so you may find that it's worthwhile either putting the Mega to sleep to save power while the bus transaction. And by the way, you can wake up on the interrupt from the 2-wire interface, or go do something else and wait for the interrupt on the 2-wire interface to come back and say that the transaction is done. Yeah. So you could put it to sleep with the TRT interface, or you could multitask off of it. You could just let this run in one thread while some other thread executes. Yes. So you'd have the interrupt signal a semaphore in TRT to say, "I'm ready." By the way, a context switch in tiny real time takes 400 cycles. It's a snoozer. It's an 8-bit machine. Yes?
And also, when you read the acknowledge bit, it is sent from the master to the slave. When the master didn't read.
Yes. Yes. It's the master doing the ACK. Yes. Or the knack in this case.
So, what was up again with the 2 write statements?
So this is the address. So the ROM is laid out as 0 through 255. It's 256 8-bit values internally. And we want to write to location 5. We want to write an FA to location 5. And so these are commands. This is the address of the ROM. This is the address within the ROM. So this is a command to the I2c bus. This is a command to the EEPROM.
And FA is the actual value.
Data that's being written in. Yeah. So this is the address. The data. It's really easy to get mixed up in levels of abstraction here, because you got everything's being addressed at the same time. Yeah, I mean, this is kind of a fake example, right? You know, we're writing it and then reading it back to make sure we can write it. I mean, that's what you'd do if you were trying to validate that you actually understood how to use an I2c bus, but it wouldn't have much other use than that. But it uses all of the interface that you need. It uses start, it uses stop, it uses start wait. It uses rep start. So it's a nice way to demonstrate the interface in a short amount of code.
Do these external EEPROMs have longer lifetimes than the ones on the system? Those are 10,000. If you're writing this in software,
So the question is, do these have a longer lifetime? So there's 2 possible lifetimes. One is the number of write cycles you can do on the EEPROM, and the second lifetime is the data retention time. The data retention time, both for the EEPROM internal on the Mega 644 and on these devices, is some long time, 10 years, something like that. Now, how they managed to keep 1,000 electrodes on a gate for 10 years, it's absolutely amazing. It's a really high resistance. But, so if these were made with bigger junctions, they would retain data better. I have no idea if they do or not. I expect that all of them are dominated by cosmic ray strikes. You strikes a transistor and you lose the data. Now, in terms of write cycles, how many write cycles can you produce? That depends on how the system is built. If it's FRAM, ferromagnetic RAM, it has 1 billion write cycles. If it's fairly low voltage flash memory, then it's 10,000 or 100,000 write cycles, or maybe 1 million. Depends on the physical characteristics of the memory, and there's no way to predict except to look at the data sheet. Yes?
What other mode can this be used apart from I2c?
Can this part? No.
No, what other mode apart from the I2c this can be used?
Oh, let me see what the mode does. I read this data sheet. It's multi-byte page write mode. So you can enable multi-byte read-write by pulling that high or low. But, yeah. Is there another hand up? So, any comments on final projects? New boards are in. I think I said this last time. I'll say it again. Also sent out email. New proto boards are in. They're a little simpler to build than the old ones. We should have all the parts. If we run out of some part, if there's some part you can't find, tell the TA or email me. Don't just say, oh well. Because it's a fairly interesting process to keep the lab stocked. It's about order n in number of parts and times m number of students, or something like that. Yes? Say again?
The parts that you ordered through you.
Parts that you ordered through me are supposed to be delivered tomorrow. DigiKey sent them on Monday afternoon for delivery Thursday. So we should see them tomorrow at lunchtime, more or less. New order will go. New order will go in Monday morning, again at 8 o'clock. So if you need something, get it ready to go. Your sum, the sum of the amount you can spend over all weeks is $20 per group. Anything else? See you in lab.